So in the third module, I will start with the hadronic calorimetry. So as we mentioned already, also hadrons, so pions, protons, kaons, when they interact with the medium, they produce a cascade of particles. The interaction is indeed dominated by strong interaction. So it's a nuclear interaction. It's not electromagnetic interaction. But you see here that when you mostly produce pions, which are the lightest hadrons, when a primary hadron interacts. And you see that so since the typical energy is large enough, then you produce pi plus, pi minus, and pi zeros in equal fractions. And then the pi zero, of course, it will decay electromagnetically, producing two photons in the final states and originating an electromagnetic interaction. So there is, of course, an electromagnetic component in any hadronic shower. Then the approximate energy distribution in strong interaction, so about half of the energy will go into this secondary particles produced in the hadron cascade. Then there will be about 20% in nuclear excitations, which will then provide particles, protons, neutrons, and photons in the MeV range. And then there will about another 30% of the energy approximately will go to slow nucleons. So if the hadronic cascade, it develops longitudinally with an absorption length, which is also called the interaction length, which is the driving parameters of an exponential function. So again, you have an exponential energy degradation with the constant parameter is the absorption length or interaction length, which is much larger than the radiation length. So, for instance, for the iron, this is about 10 times larger. For the lead, this is even more, is about 30 times larger. So, for the energy resolution, well, one can easily understand that since a large fraction of the energies disappears somehow in binding energy of the emitting nucleons, on some of the neutrinos which can fly away after the pion decays. Then it is clear that you have an energy resolution which is worse than electromagnetic calorimeters, clearly, because then here you have only the pi zero part, which is electromagnetic. All the rest is somehow undergoes to a certain number of losses. Then this kind of device, they are much bigger than electromagnetic calorimeters because of the lambda, which is about 1 order of magnitude, typically 1 order of magnitude larger than the radiation length. And so it is clear that they have to be much larger to get the similar containment of the showers. So it also, the energy degradation proceeds through an increasing number of strong interaction, mostly with the material of the calorimeter. However, the complexity of the hadronic and nuclear processes, it produced a huge number of effects which can influence the functioning and the performance of the instruments, and so they make the hadronic calorimeters much more complicated than electromagnetic ones. So hadronic interaction, they produce actually two classes of effects. So at first these secondary hadrons are produced, and they momenta are a sizable fraction of the primary momentum. The second effect is that in hadron collisions you have a significant part of the primary energy which is somehow spent in nuclear processes such as the excitation or the nucleon evaporation, the spallation, which results into particles on the MeV scale. So therefore, this excitation and this MeV scale effect, they do not actually produce a signal in your detector, and so part of this energy is invisible. And so this makes actually, as we said, the typical resolution of hadronic calorimeters worse than electromagnetic ones. And so this is more in the range, let's say, from 20 to 100% of the square root of the energy. So, and you see that what is the typical variety of processes which are produced in an hadronic interaction. And you see that you produce secondary pions, you produce electrons, you produce photons, you produce protons, but then you produce also neutrons. So there are so many processes that you have to account, which somehow explains why these instruments are much more complicated than the usual one. Then the signal from an electron or a photon is typically much larger than the signal from a hadron cascade, because of this effect of the invisible part of some of the energy due to excitation, evaporation of the nucleons, and so on. And so it is clear that you have a larger signal from an electron than from a hadron, even if they start with the same initial energy. So you have to account for this invisible energy and compensating this part. So moreover, we know that a large fraction of the energy, in particular a large fraction of the visible energy, goes to pi 0, because as we said, basically you have pi plus, pi minus, and pi zeros on equal footing, and they share 1/3 of the energy. And so part of this hadronic cascade becomes an electromagnetic cascade. And this, of course, will never come back as hadrons, because then the pi 0 decays immediately in 10 to the minus 16. It's the typical lifetime of pi 0 to 2 photons, and then the photons will lose their energy in producing a shower. And so then you have a larger response for the electromagnetic cascade than for the hadron cascade. And this will produce somehow strong degradation of the resolution, because you have a component of the shower which produces a signal which will produce more hits for the same energy compared to the other component of the shower. And so the question is whether it is possible to build a calorimeter which provides the same response for a 10 GeV electron and for a 10 GeV hadron. So the answer to these questions is yes, and it is possible, and this is what compensating calorimeters do. So they are called compensating because they actually compensate for the different response of a hadron and of the calorimeter to a hadron and an electron of the same energy. So in a homogeneous calorimeter where you have only an active medium, it is clearly not possible to have the same response for electrons and hadrons because they will propagate in an active medium, but you will not see part of the energy, and so the signal will clearly be different in the two. For sampling calorimeters, actually the sampling frequency and the thickness of the active and passive layers, they can be tuned in such a way that the signal for electrons and hadrons is indeed the same. So using uranium or lead with scintillators, then one can make hadron calorimeters with excellent energy resolution and with a very good linearity in the response. So one can actually make a compensating calorimeter, and this was somehow built and demonstrated. So the resolution and the linearity of a hadron calorimeter is of course the best if this ratio of the electron to a hadron response is 1, and then the resolution and the linearity that gets clearly worse if this is not the case. So the calorimeters, they are normally part of a larger system in the experiment, which is the particle identification system, because it is clear that, for instance, they have a very different response to different particles. So if you have photons, then you have nothing at the entrance. Then you start having a shower, an electromagnetic shower. And so if you have a tracking system in front, you will not see any particle for a photon, and then you will see this showering in your electromagnetic calorimeter. So for the electron it will be similar, except for a charged particle incoming, and therefore you will be able to distinguish between photons and electrons. The muons will be a penetrating particle, I mean, unless its energy is really above on the TeV scale, but otherwise this will not produce any shower, but will simply be passing through, because most of the energy will be for ionization and not will be released for ionization and not for Bremsstrahlung, because you are below the critical energy. While then if you have protons or charged pions, then you have you will see the track in the tracking system and in front. Then you will see this showering, but on a much longer scale, which is driven by the absorption length, and so you will need an electromagnetic and hadronic calorimeter to perform the energy measurement. While if you have a neutral hadron, then you won't see any particle in the tracking system in front, and then you will start seeing a signal in your calorimeter. But then if you have a muon system downstream, only the muon will actually reach your muon system, so you can identify the muon with by counting how many particles actually they survive your calorimeters. you identify the muons, and then you may use then you have to use a magnetic spectrometer to measure its energy, since it doesn't produce a shower. So what happens when you have neutrinos? When you have neutrinos interacting, so this is the schematic drawing or the event display of a real event or a real neutrino interactions happening in the Opera experiment, and you have this single track coming out. And this track is a muon, is a penetrating muon, and basically you have the muon in the final state, well, plus some hadronic jet. In this case, the hadronic jet is very much limited because this is a quasi-elastic muon-neutrino interaction. So the issue is, how do you measure the energy? Then, in this case, of course, part of the energy will go to the charged lepton, and you have to measure the momentum of the muon. This you do with magnetic spectrometers. There's no other way. But then you have to measure also the hadronic jet when this is relevant, of course. So for the deep inelastic interaction, you have a large fraction, typically half of the energy, which goes to the hadronic jet, and the other half goes to the charged lepton. So and so you see here what is the typical multiplicity of charged particles produced in a neutrino interaction in Opera, and so you have on average 3.4 tracks per each interactions, and the typical energy, the mean energy, is about 24 GeV, and on the right you see that roughly half of this energy is taken by the muon coming out, and so you actually have to, we were using, in order to measure the hadronic jet, there's the energy deposition in the target trackers was used. So we had scintillating bars as a target tracker in between different brick walls, and these actually were used to estimate the energy released in the target. So before calibration, you see that this energy is, this is just the energy released in the sensitive planes, which is of course a tiny fraction of the overall energy, because indeed, as we said, this will work as a sampling calorimeter, but where the most of the mass is indeed in the emulsion cloud chamber, and so then only a small fraction, you see, is indeed expressed in MeV, so it's less than 1 GeV. While after calibration, you can turn this energy released in the target trackers into the overall energy, and then you see the bottom plot. This shows the momentum of the muon, which is also the second ingredient to build up the energy, the total energy of the event, because then you have the hadronic jet, which is very well reproduced, very well measured, and is shown in the top plot, and then the muon energy is also very well measured. This is the muon momentum times charge, so this is measured both for negative muons, which are the majority because they come from muon neutrinos, and for positive muons, which come from muon antineutrinos, which is only present as a small contamination at the level of 2%. And so if you put everything together, if you put together the momentum of the muon and the energy of the hadronic jet after suitable calibration, then you end up with the energy measured here, and you see that this is very well reproducing the data, and then based on this energy you can actually also describe the different components, because there are deep inelastic charger current, deep inelastic interaction, there are neutral current interaction, there are quasi-elastic and resonance interaction, and you see that data are very well described by the Monte Carlo simulation. Then there's another project which is now being launched at CERN, the scattering and neutrino detector operating at the LHC. It is called SND at LHC, and this is also a neutrino detector meant to measure TeV scale neutrinos, and this will combine electromagnetic calorimeter made of a combination of emulsion and Sci-Fi, and hadronic calorimeter made by the combination of Sci-Fi planes and scintillating bars. And then you end up with an hadronic energy resolution at the level of 20% with this kind of detector. It will start taking data in 2022 at the LHC at CERN. And so in conclusion, so the story of modern calorimetry is a textbook example of research in physics which is driven by the development of an experimental method. So it's extremely important to measure the energy of particles in order to make also discoveries, and so it was extremely important, for instance, to measure the energies of the photons for the discovery of the Higgs particle. And so then calorimeters are also largely used in neutrino physics, because you want to measure the energy of the neutrinos interacting in your detector. So I leave you with a couple of quizzes and also with homework. Thank you.